This is a past HSC trial exam question on special relativity. So suppose you have a planet P and an astronaut wants to go from Earth E to planet P. On a spacecraft. So the spacecraft will be launched from Earth and it wants to travel at a speed of 0.8 c, in other words, 80% the speed of light. And the journey is expected to take 15 years, according to the guys on Earth watching the astronaut. Let's suppose we need to work out determine the distance to the planet P in meters as measured by observers on Earth. 2 marks. Okay. All we need to use here is the formula distance is velocity times time. The velocity is what we're given. That's 0.8. We're going to express it in terms of light years. So 0.8 times 15. Okay, 15 years, and that's 12 light years, L sub y. Okay, now important note, a light year is not a measure of time, it's a measure of distance. It's how the distance covered by light, distance light travels in 1 year. Now to convert this into meters, we'll go 12 light years times 3 times 10 to the 8. Okay, that's the speed of light, times 365 days, times 24 hours, times 60 minutes, times 60 seconds. That's 1.14 times 10 to the 17 meters. So 1 mark for working out, 1 mark for the answer. Second bit, so that's A. Let's do B. Use time dilation to show that the astronaut will be observed to age only 9 years while traveling. 2 marks. Time dilation, whenever you hear the word time dilation, go straight to your formula sheet. Here's the formula. We need to work out T sub naught, okay? Because in the astronaut's reference frame, so T sub naught is the proper time, so the time measured by the guy that's in the spaceship, okay? According to him, he's stationary, everyone else is moving, right? So the astronaut's frame of reference, T sub naught is then T times the square root of 1 minus V squared over C squared. Now T is 15. 15 years is measured by the guys on Earth, right? So they're saying 15. We need to show that he's aging by 9 years. In other words, he experiences 9 years of travel as opposed to 15. Times square root of 1 minus 0.8 squared, and you'll get 9 years. That's time dilation. Moving clocks run slow. Faster you move, the slower time goes for you. So 9 years, 1 mark for the working out, 1 mark for the answer. Part C. Okay, the astronaut isn't expected to experience time dilation within their frame of reference. Explain why the astronaut will still expect to age only 9 years on the journey. Use calculations to support your answer. Okay, this is a 3 marker here. Okay, the way you go about this is that if the astronaut isn't expected to experience time dilation, then he will be expected to experience length contraction. So in astronaut's frame of reference, the distance to the planet P is contracted. The distance between Earth and the planet P is contracted via length contraction. That's the formula. So the length, so in the astronaut's frame of reference, he sees the length L contract. Okay, this is the astronaut's proper length. Okay, and that's 12 light years. Okay, according to the observers on Earth, they say 12 light years. This ratio here is this expression is 0.6, so 12 times 0.6 is 7.2 light years. Now, based on this distance, the journey time measured by the astronaut is given by this. T is distance divided by velocity. That's 7.2 light years divided by 0.8. That's the astronaut's speed in terms of the speed of light. It's about 80% of the speed of light. And that gives you indeed 9 years. One mark for the correct working out here, one mark for the correct working out here, one mark for the correct answer. And that's how you do this question.